integral calculus was initially used for finding areas under curves. And the Greeks used integration, ideas of integration, before derivatives even existed. So we learned derivatives first because it's easier to learn the easy one first and then the hard one after. But the ideas of integration existed before derivatives existed. And then it's just sort of like these two different ideas came together and they're like, oh my goodness, they're related. So, first, we've got Greek mathematicians who used the method of exhaustion to find areas under curves. This sounds very tiring, doesn't it? The method of exhaustion. The method of exhaustion looks like this. If you had a sine curve like this, and you wanted to find, ooh, I'm going to use a nice crayon to color this in. You go, oh, all right, here we go. If you've never colored with crayon on a smartboard, you should take some time and come. It's just, it's something feels good about coloring with a crayon. You can almost smell the wax. There we go. If I wanted to find that area, that would be hard because you have no formula on your formula sheet ever that's like, oh, that's, yeah, that shape. No, it's not easy. So what the Greeks did as their method of exhaustion is they said, I do know the area of a rectangle. So if I do this, I will get an area, and that area will be too big, but I might be close. Right? Would you agree that if you did the green area, it would be too big, but be close? But another guy says, well, what happens if I did littler rectangles? Just like this, all the way along. Just always took the higher point and made a rectangle across. You see that this is still too big, but it's closer. Right? And that mathematician said to the other mathematician, haha, I got closer to you. Well, you can see why this is going to get exhausting. Because if I made my rectangle smaller, I'd be closer than you are. And then you go back and be like, well, I'll make my rectangle smaller than your rectangles, and I'll be closer than you. And if we keep getting smaller and smaller rectangles, eventually the limit, right? They didn't talk limits, but they had the idea that eventually you're going to get closer and closer to the actual area. This is the method of exhaustion. And a famous mathematician, Archimedes, is considered the father of integral calculus because he was already doing this. And we're going to find out that this later connects to derivatives, which is like, how does area under curves connect to tangent lines on slopes? So first, we talk about anti-differentiation. This is not people opposed to differentiation that have like strikes and things like that. It just means the opposite or reverse process of differentiation. So if you have a derivative, the antiderivative or integral is what the original function was. And in our notes with Mr. LaFrance early in the year, we already had like snuck in a little bit of anti-differentiation when you didn't notice. It's like, oh, do you think you could work backwards and find out what the original one was? We were already planting the seed of this idea. So it was like, hey, the derivative is 2x. What's the original function? That's x squared. Perfect. But it could have also been x squared plus 2. Because if you did the derivative of x squared plus 2, what would happen to the 2? It just disappears. Could have been x squared minus pi. And so when we do the antiderivative, there's actually an infinite number of right answers. Does that make sense? Because it could be plus or minus anything. So sometimes you'll see, and you'll be asked to just say, it could be anything, where C can be any real number. But if it just asked you to find one of them, I'd probably just stay with x squared plus 0. That seems easy enough. But it could have had another number there. Right? So there's an infinite amount because the derivative of any constant number would be 0. So no, whenever you work backwards, there could have been a plus 7 at the end, or whatever your favorite number is, you could have had that there. So we have no way of knowing if there was an extra number unless the question, there will be some questions where they give you additional information. Like, this was the derivative. Can you find the original function if it also happened to pass through the point 3, 7? And if it goes through 3, 7, then you have a way of figuring out what number would have been at the end. So we'll do questions like that. But here's this idea. So if your derivative is this, then your original function will have a plus c, where c could be any number in the real numbers. And we call that the antiderivative. And the set of all antiderivatives is called the indefinite integral. And it's indefinite because you're not sure what that c is. That's what makes it undefined a little bit. The indefinite integral. And we write it with this fancy, you make these fancy little symbols. Oh, some fun. They're really, this one is kind of disappointing. They're actually longer than that. They're like, and they always have this to tell you what variable you're antiderivating with. I don't think that's a word. You're integrating with. So in this case, if my variable is f of x, and that's what I did the derivative with, then the dx there tells me that's the variable you're going to underderive with. So the set of all antiderivatives 2x is this x squared plus c, where c is any number. So some definitions. That's our integral sign. The inside is called the integrand. The x is the variable of integration. So like this, dx says, can you integrate with regards to x? And then c is the constant of integration. So I have this little diagram, which I don't know if you can read anything on yours. We did a wonderful job with the photocopier and making it nice and small. Can you read anything on yours on the next page? A little bit? Your eyesight is definitely better than mine. So you have your function, you could do the derivative to go one direction, you do the antiderivative to go back. Right? Or you could say a function in the middle, if I go backwards, I get the antiderivative, forwards, I get the derivative. Just the idea of the process that you're going. So now we have to develop rules. The undo rules. What's your rule for power law? Like if you were asked to do the derivative of this, you bring the 5 out in front, subtract 1 from the exponent, right? So 5 comes out in front, subtract 1 from the exponent. Perfect. Now if you had to create a rule for working backwards, okay? Now you have these, I think these are examples actually from first semester notes. if you had 5x to the 4, you probably can just see right away that it would be x to the 5. And in first semester, you would have done that immediately. I'm going to tell you that you're going to learn a process and you're going to stop doing that. You're going to actually do this instead. Tell me if this is a different answer. This is how you're going to write it. It's the same answer. But your thought process is a little bit different. So, when we started doing this, you saw it as a holistic picture. You saw what would happen, and you undid it, right? But if we think about undoing these steps, wouldn't you undo step 2 first, and then undo step 1 after? So undoing step 2, which was subtract 1 from the exponent, you see, when I was writing it, the first thing I did, I didn't worry about the 5, first thing I did was I added 1 to the exponent. And then, if my first step in derivatives was multiply by the exponent, to undo multiplying by the exponent, I divide by my exponent. And that cancels out the 5 and gives us the same thing. But where this is nice, like, on this one you did some mental math, right? You would have probably just immediately said, I know that it's 4x cubed. Our new process is going to say, well, first I'm going to add 1 to the exponent, and then I'd have to divide by that to cancel out the multiplying. And I'll write it like this instead. It's the exact same answer, but where this process is nice is when I would give you something where the mental math would be, ugh. Can I give you a mental math that you'd be like this one? Probably did this mental math no problem, right? The first one, for sure. It's like, what happens if I gave you work backwards and I said dy dx was 5/3 x to the 7/13? Okay? Let's just quickly mental math it and tell me what the answer is. Like, oh! Okay? But the new process would say, don't worry about the 5/3. Add 1 to the exponent. You know how in derivatives you got really good at subtracting by 1? You're going to get really good at adding by 1. These are skills that you thought you had down pat before you got into AP Calculus. But not. AP Calculus has taught me I'm really good at subtracting by 1 and adding by 1. So now, you add 1 to this, and what would you get? You would get 20/13, which would mean you'd have to divide by 20/13. And if you wanted to, you could simplify this by multiplying, right? Dividing by a fraction is the same as multiplying by the reciprocal, so you get 65/60. Yes?
I don't know if you noticed, but you changed the x to a y.
Change the x. Oh, I did. That's fascinating. That's terrible. Wait for it. I think I've got. No, that doesn't even look good. I was trying to do some sort of fancy save, but it was disastrous. There we go. And that's 65/60. If you wanted to, you could reduce that to. Now. In all the other ones, you could go directly to the answer. This one wasn't so easy to go directly to the answer. So having an undoing process that's not hard actually made it easy. So if our power rule says we subtract 1 from we multiply in front and then subtract 1 from the exponent, now to undo that, we'd have to add 1 to the exponent and divide by our exponent. And things work out nice. So, step 1, add 1 to the exponent. Opposite of subtracting 1 from the exponent. Step 2, divide by the new exponent. which was the opposite of multiplying the function by the exponent. And then we have to add, if we want to do all of the antiderivatives, we'd have to add c, say a plus c, because it could have been anything. Now notice these questions that you had from previous units, the wording was find a function. So you didn't have to find them all. You just had to find one that worked. Right? If you have a favorite number, does anybody have a favorite number? Neil, do you have a favorite number?
7.
7. So you could take advantage of this situation and add a plus 7 to that question. It says find a function, and there's your opportunity to add that 7. Right? You're like, ooh, another one, find a function. I'm going to add 7 to this because I like the number 7. That would be still right. But if it said find all of them, then we're going to have to do plus c and every single time. So sometimes on the integration test, I have students right at the top of their test write plus c. Don't forget, because we don't want to lose those half marks because you forgot the plus c. So now we get to general formulas. And I have a whole booklet of general formulas that I'm going to give out to you once we've undone all the derivatives we've done so far. Have we done lots of derivatives so far? Yeah, you have to undo them all. Okay. First one, we did. Add 1 to the exponent, divide by your new exponent. Remember the plus c. Why can't n be negative 1?
Make it a 0 on the bottom.
Make it a 0 on the bottom. So like, sorry, I'm gonna have fun with this. So if I have x to the negative 1 dx, what's the answer? Because if you add 1 to the exponent, that would give you 0, and then you have to divide by 0. This is bad. And this is a great example of why integration is harder than derivatives. Because you should know, should I pretend to be mad? You should know the answer to this. But you're all just sitting there quiet. That should be absolutely, I'm gonna, you know what? I'll get mad at this one. It's probably this one. It's not yours. It's hard because your brain, all the way through with derivatives, was triggered to see something move forward. But you never taught yourself to see something step backwards. What derivative has this? What has this as a derivative? Should I make your life a little bit easier? Just somebody might, okay, we got someone who might have seen it. I'll rewrite x to the negative 1, I'll rewrite this. Does that help you? Natural log of x. The answer is the natural log of x plus c. We've got a little bit of a problem because here x could be negative, here x can't be negative. We actually, in integration, then have to add absolute value bars. Well, it's coming up in a minute. Your brain is already hurting. I know. This is wonderful. So you see why it makes it more difficult, right? Because this, if I said, what's the derivative of natural log? Most of you would have been like, oh yeah, it's 1 over x. Some of you would be like, yeah, I forgot that one too. That's okay. But now you have to know it so well so that you can recognize it to work backwards. All right, I jumped ahead. So, if you have a number in front, that number just stays out in front. It doesn't matter. So, if you had this 11x to the 5, I think this is one where the mental math doesn't become easy. You're just looking at it, but using our new steps. Add 1 to that exponent. Then divide by your new exponent. I'm pretty sure on the exam, if you don't write this if you just do plus C, people kind of understand that you mean everything. You don't define it that C can be any real number. I'm not gonna get super fussy about that on your tests. I'll double check for your exam if they're fussy about that. All right. So, sum to try. You've got 1, 2, 3. 3 to go before the bottom of the page. And what I tried to do with each of these examples was I tried to find a different way I could word the same thing, just so you get used to, like this one says integrate with respect to x. I tried different notations to show you all of them mean the same thing.
Interruption, staff and students, at dismissal, please, staff, we are going to meet in the theater for today, so make sure you make your way as soon as possible to the theater once classes are dismissed this afternoon. Thank you.
How's your adding 1 skill? Okay, which, I mean, as simple as the idea is of adding 1 and subtracting 1, as soon as you have to do one or the other, you're now going to start messing yourself up and going the wrong direction sometimes. Can you see that happening? Especially with negatives. Oh my goodness. Like when you add 1 to a negative, it goes from a 3 to a 2. Oh no. That hurts the brain a little bit, right? Square root of x. You might take a little bit of time to change it to an x to the half. Because then you can add 1 to the exponent and divide by your new exponent. And what's really nice about this technique is you don't get bogged down in trying to like figure out the mental math. Sort of like you just do a process, added 1 to the exponent, divide, and then you're like, oh, I could simplify this if I wanted to. And I get 20/3 out in front. Which might not have been easy to see if you were just trying to do the mental math from the beginning. Here's some interesting notation. Find the indefinite integral of y dx. So the dx says that the variable that we're working backwards with is the x. But here there's a y. So the first thing I'm going to do is if I know this is what y is equal to, I'm going to plug that in instead. So then I get x, and I'll change the 7th root to a 1/7 as an exponent. And then I can add 1 to my exponent and divide by my exponent. multiply by the reciprocal. And we get our answer.